The universe we live in is deeply strange. It contains phenomena so vast and extreme that the human mind struggles to comprehend them. Reality extends far beyond everyday intuition. There are structures stretching hundreds of millions of light years. There are events so violent they push the laws of physics to their limits. Galaxies are woven into colossal cosmic webs. Explosions can briefly outshine entire star systems. Some worlds burn hotter than molten metal. Other moons are colder than liquid nitrogen. At the very edge of existence lies a boundary we can never cross. It is called the observable horizon. Beyond it, information is permanently lost. Facing these ideas forces us to admit how small our understanding truly is. What unsettles us most is not danger, it is uncertainty. And few cosmic visitors have embodied uncertainty more completely than Oumuamua. This was not just another wandering rock. It was an interstellar traveler, the first object ever detected passing through our solar system from another star system. It was discovered in 2017. By the time we noticed it, it was already speeding away. It was moving at roughly 26 kilometers per second relative to the Sun. Its origin remains unknown. No one knows which star it came from. No one knows what event launched it into the emptiness between stars. What we do know is that Oumuamua was unlike anything seen before. Its shape appeared extremely elongated, possibly 10 times longer than it was wide, more like a spinning baton than a typical asteroid. As it tumbled through space, it reflected sunlight in a strange way. This suggested a highly unusual geometry. It showed no visible comet tail, no cloud of gas, no dust. Yet its trajectory changed slightly as it left the solar system, as if something invisible were pushing on it. Some scientists suggested that hydrogen ice or nitrogen ice was slowly evaporating from its surface. Others proposed more exotic explanations, including artificial origins. Extraordinary claims require extraordinary evidence, and the truth remains simple and unsettling. We do not know what it was. Oumuamua gave humanity a brief glimpse of material from another stellar neighborhood, and it reminded us how little we understand about what drifts through the Milky Way. At the center of that galaxy lies something more familiar, yet equally mysterious. The core of the Milky Way is dominated by a supermassive black hole. It is known as Sagittarius A star. Observations of nearby stars reveal its mass, about 4 million times the mass of our Sun, compressed into a region roughly the size of our solar system. Stars near the center orbit at thousands of kilometers per second. They are held by a gravitational pull so intense that not even light can escape. Once light crosses the event horizon, it is gone forever. Inside a black hole, our understanding of reality breaks down. Time loses meaning. Space loses structure. According to general relativity, anything falling inward is stretched into long, thin strands. This process is known as spaghettification. All paths lead toward a singularity, a point of infinite density, a place where our equations fail. We do not know what truly happens there. Our best theories stop working. New physics is required. Even more unsettling is this. There appears to be no upper limit to the size of a black hole. Sagittarius A star is enormous, but on a cosmic scale, it is modest. One of the most extreme black holes ever observed is called TON 618. Its mass is estimated at about 66 billion suns, more massive than many entire galaxies. Its event horizon would span hundreds of astronomical units. Fortunately, it lies around 18 billion light-years away. far beyond any realistic threat. Objects like this challenge our understanding, how black holes grow, and how much matter the universe can compress into a single point. Thinking about such extremes naturally leads to human exploration. Becoming an astronaut is not just about physical strength. It is not just about technical skill. It requires a mindset built for uncertainty. Veteran astronauts often describe their training in simple terms: learning how to stay calm when the unexpected happens, the ability to adapt, to analyze problems step by step, and to keep learning under pressure. These skills matter in space, and they matter just as much on Earth. Breaking complex challenges into manageable parts is a survival skill in orbit. It is also a powerful way to navigate everyday life. This is how scientists face the unknown, not with fear, but with patience, with curiosity, and with determination. As stable as our galaxy may feel, it is anything but static. The Milky Way is locked in a slow gravitational dance with its nearest large neighbor, the Andromeda galaxy. Andromeda is approaching us at about 110 kilometers per second in roughly 4 to 5 billion years. The two galaxies will begin to merge. This will not be a dramatic collision of stars smashing into one another. Space is far too empty for that. Instead, the galaxies will pass through each other. Their shapes will stretch and warp as gravity reshuffles billions of stars. From the surface of Earth, if it still exists, the night sky would slowly transform into a chaotic swirl of light. By that time, however, the sun itself will be nearing the end of its life. But even this future merger is only part of a much larger motion. Our entire local group, roughly 1,000 galaxies, is drifting toward a mysterious region of space. It is known as the Great Attractor. This unseen influence lies in the direction of the constellation Norma. Its gravitational pull is strong enough to affect galaxy clusters across hundreds of millions of light years. We cannot observe it directly. It sits behind the dense dust and stars of our own galactic center. Astronomers call this region the zone of avoidance. Current evidence suggests the pull comes from an immense concentration of matter. It is called the Shapley supercluster. This structure contains on the order of 100,000 galaxies. Its mass is so vast that it continues to draw in surrounding structures, growing larger over time. Opposite these crowded regions are vast expanses of almost nothing. One of the most striking is the Boötes Void. It lies about 700 million light-years away. This region is so empty that it contains only around 60 galaxies. Thousands would normally be expected. The void spans roughly 330 million light-years across, making it one of the largest known voids in the observable universe. These enormous gaps likely formed from tiny fluctuations shortly after the Big Bang. Over billions of years, those differences expanded. Why these regions remain so empty is still an open question. Taken together, clusters and voids reveal something remarkable. The universe has structure, almost like a cosmic web. Some researchers have noticed something even more intriguing. On the largest scales, the distribution of galaxies resembles the network of neurons in a human brain. This may be coincidence, a trick of pattern recognition, or it may hint at deeper principles shaping reality. Either way, the resemblance is enough to inspire awe. And as strange as these immense structures are, the universe often surprises us on smaller scales. In 2009, astronomers were monitoring a massive star in the constellation Cygnus. It appeared to be nearing the end of its life. Over just 3 months, its brightness increased by nearly 1 million times. All signs pointed toward an imminent supernova, an explosion capable of releasing more energy in seconds than our sun will emit over its entire 10 billion year lifetime. Then, without warning, the star vanished. There was no explosion, no lingering glow. Its star simply faded from view. Whether it collapsed directly into a black hole or failed in some unexpected way remains uncertain. A reminder that even well-studied processes can still defy expectations. When astronomers talk about the death of stars, the process often sounds mechanical, governed by well-tested physics. A massive star spends millions of years as a gigantic nuclear furnace. Hydrogen fuses into helium, releasing enormous energy. That outward pressure balances the inward pull of gravity. Over time, the fuel changes. Helium fuses into heavier elements: carbon, oxygen, neon, silicon. Eventually, iron. Iron is the end of the line. Fusing iron consumes energy instead of releasing it. Once the iron core reaches about 1.4 times the mass of the Sun, the Chandrasekhar limit, gravity wins. The core collapses in a fraction of a second. The outer layers crash inward, rebound, and are blasted into space. A supernova is born. For a brief moment, one star can outshine an entire galaxy. The shock wave races outward at thousands of kilometers per second, releasing on the order of 10 to the power of 44 joules of energy. Anything within roughly 30 to 50 light years is stripped of atmospheres and bombarded with radiation. What remains is either a neutron star, packing more mass than the Sun into a sphere about 20 kilometers wide, or, if the core is heavy enough, a newborn black hole. This is why the disappearing star in Cygnus was so unsettling. It appeared to skip the explosion entirely. Instead, it may have collapsed straight into a black hole, a so-called failed supernova. If confirmed, this would mean some of the most massive stars die quietly, leaving behind almost no visible trace. That possibility forces astronomers to rethink how many black holes may be hiding in the galaxy. Our next chance to witness a stellar death up close may come from a familiar name: Betelgeuse, the red supergiant marking the shoulder of Orion. It lies about 650 light-years away, and it is roughly 700 times larger than the Sun. If placed at the center of our solar system, its outer atmosphere would extend beyond the orbit of Mars. When Betelgeuse finally explodes, it may shine as brightly as the full moon, for weeks, or even months. Despite how dramatic it will appear, Earth will be safe. At that distance, the energy will be too spread out to cause harm. The only frustration is timing. Near the end, in stellar terms, could still mean another 100,000 years. One of the most fascinating things about space is that extreme weirdness is not limited to distant galaxies. Our own solar system is filled with alien environments. Saturn's moon Titan is a perfect example. Titan is the second largest moon in the solar system, about 5,150 kilometers in diameter. It is larger than the planet Mercury. Its gravity is strong enough to hold a thick atmosphere, mostly nitrogen, with traces of methane and ethane. At the surface, temperatures hover around minus 180 degrees Celsius. At those temperatures, methane behaves the way water does on Earth. It evaporates. It forms clouds. It falls as rain. And it flows across the landscape in rivers and lakes. Radar images from the Cassini spacecraft revealed vast methane seas near Titan's poles. Some of them stretch hundreds of kilometers across. This makes Titan the only other known world, besides Earth, with stable liquid on its surface. The chemistry is completely different, but the processes are eerily familiar. They suggest that nature may reuse the same physical rules, even in wildly different environments. Now imagine the opposite extreme. Instead of a frozen world, picture a planet so close to its star that its surface literally melts. Kepler 10b is one such world. It lies about 560 light-years away. It is roughly the same size as Earth, but it orbits its star at a distance of only 0.02 astronomical units, around 20 times closer than Mercury is to the Sun. As a result, its dayside temperature likely exceeds 1,300 degrees Celsius. At those temperatures, rock does not behave like rock anymore. The surface would be covered in oceans of molten lava. Even more bizarre, the intense heat could vaporize that lava, sending rock vapor into the atmosphere. As the vapor cools, it would condense and fall back to the surface as liquid stone, lava rain. It sounds like science fiction, but it follows directly from known physics under extreme conditions. As strange as individual worlds and stars can be, the most mind-bending ideas appear on the largest possible scale. Space itself may be infinite, stretching endlessly in every direction. Yet there is a limit to what we can observe. This boundary is called the observable universe. Its edge lies about 46 billion light-years away, in every direction. This may seem contradictory. After all, the universe is only about 13.8 billion years old. But cosmic expansion explains the difference. While light has been traveling toward us for billions of years, the space it moves through has been expanding at the same time. The speed of light, about 300,000 kilometers per second, is the fastest speed at which information can travel. But space itself is not bound by that limit. Since the Big Bang, the expansion of the universe has been accelerating, driven by a mysterious influence we call dark energy. At great enough distances, galaxies are being carried away from us faster than light. Not through space, but because space itself is expanding. Light emitted beyond a certain distance will never reach Earth, no matter how long we wait. This has profound consequences for the future. As expansion continues, more galaxies will slip beyond our observable horizon. Tens of billions of years from now, the night sky will appear emptier. In about 1 trillion years, observers in our galaxy would see no other galaxies at all. Only the stars bound to the Milky Way would remain visible. Even that future is temporary. Long before then, the sun will exhaust its fuel. It will shed its outer layers and leave behind a dense white dwarf. This leads to one final, unsettling idea: deep time. The universe does not end when we do. It continues for billions, for trillions, and perhaps for infinite years. Galaxies merge and fade. Black holes slowly evaporate over timescales of 10 to the power of 100 years. Space grows colder, darker, and quieter. In that context, humanity's entire existence occupies only a thin slice of cosmic history. And yet, within that brief moment, we are able to look outward. We detect interstellar visitors. We map black holes. We predict stellar deaths. And we glimpse the edge of reality itself. The universe is strange, often unsettling, and vastly beyond us. But for a short time, we are here to wonder about it.